This is a short video introducing the ECCV2022 paper, AirDet Fuel Shot Detection Without Fine-Tuning for Autonomous Exploration, conducted by the Air Lab at the Robotics Institute in Carnegie Mellon University. This presentation will first give a brief introduction to the motivation, and the key ideas about the model architecture is shown in the methodology. Finally, we display experimental results. Fuel shot detection aims to detect the out-of-training set novel classes with just a few samples. As we see in the figure, during robotics exploration, there are some interesting objects like ropes, fire extinguishers, and vents. These are uncommon and unseen in the existing general training set, like COCO. To detect these unseen objects with just few online annotated data, we expect a fuel shot detector. However, as is shown in the left figure, after base training, existing methods have to be fine-tuned before inference. Such a paradigm has two problems for robotic exploration. First, the interesting novel classes in the unknown environment is dynamic. If we fine-tune every time we change the classes, it will be too time-consuming for exploration tasks like rescue. Second, the hyperparameter for fuel shot fine-tuning, like learning rate, can't be determined during exploration where there are no validation datasets. To solve these problems, we designed a new model called AirDet, which can be directly deployed after base training. As we see on the right, AirDet can work without fine-tuning even better than the carefully fine-tuned models. Next, I'll introduce the key idea of our method. The working pipeline is shown on the right. A robot explorer captures some potential interesting raw images and sends them to the human user. The human can online annotate the novel objects and send these annotations back to the robot. After that, the robot can detect these novel instances in the following new inputs. We present the high-level architecture of AirDet on the right. The annotated support images and query images are first fed into the shared backbone for visual feature. With multi-scale support box feature and multi-scale query feature, we propose support-guided cross-scale fusion model for generate proposals. With the deepest support feature, we propose short aggregation module, which is based on relation to construct a strong class prototype. With the class prototype and the region proposals, we propose a fully relation-based detection high, including regression and classification to get the final result. Three key modules of AirDet are all based on class-agnostic relation. We define two types of class-agnostic relation, namely spatial relation and channel relation, respectively. For spatial relation, consider two tensors, x and y. We first squeeze x into one-by-one convolutional kernels. We then apply depth-wise convolution between x and y to obtain g, which represents the deep spatial similarity of tensor x and y. For channel relation, consider two tensors A and B. We first concatenate them along the channel dimension. The two sub-branches, convolutions, are employed. First is standard convolution. Second is the grouped convolution. We finally add these two streams to get the channel relation between A and B. For details of how the relation builds up AirDet, please refer to our paper and code. Next is our experimental results. We use COCO 2017 dataset non-VOC classes as training set. We test the model on COCO VOC classes, Pascal VOC dataset, Levis dataset, and the real-world exploration data from DARPA challenge. The highlight is that we use the same trained model for all the settings. Our model without fine-tuning can achieve SOTA performance. With fine-tuning, we have outperformed the current SOTAs. Trained on COCO, we perform cross-domain tests on Pascal VOC dataset. It can be seen that the SOTA methods usually can't perform well in cross-domain setting, and AirDet, without fine-tuning, can show promising generalization capability on the cross-domain tests. In DARPA challenge, we collected a total of 12 sequences with different lengths. In each sequence, we have outperformed our baseline method. We finally display some qualitative results here. In a DARPA challenge, the environments are complex and cluttered, where our method can perform robustly under illumination variation, partial occlusion, scale change, and motion blur. We believe AirDet can push the fuel shot detection in robotics forward in the future. Thanks for listening.